So our next speaker is Lauranne, who is going to be telling us about jet feedback on the hosts of radio galaxies.
Thank you. All right. Okay. So yeah, I'm going to be talking to you actually about a set of radio galaxies where we've got good indications that the jet is interacting directly with the ISM. And the question that we want to ask is, well, what is the effect that that interaction is having on the star formation activity in these galaxies? So what we can immediately start to ask, and what I'm sure is immediately the question in your mind is, well, how do you know the jet is having an impact on the interstellar medium? And the way that we know it is based on the Spitzer IRS spectra of these guys and the fact that they all fall, they all fall in a class of galaxies called warm molecular hydrogen emission galaxies, or warm H2 luminous galaxies. And so in the Spitzer IRS bandpass, I'm showing you a spectrum of one of these from one of my galaxies. You can have a whole slew of these molecular hydrogen lines. These are 0, 0, purely rotational lines. And you start with the S0 line at about 28 microns. And for some of these guys, you can go down all the way to the S7 line, down there at near 5 microns, the strongest of the lines being the S1 line, and about 17 microns. So for all of these galaxies, we compare the luminosity that's coming out in the S0 to S3 line to the luminosity that's coming out in the PAH 7.7 micron complex. And the reason we do this is because the H2 molecule can be excited by UV photons from star formation, as can the PAH small molecules. But once that ratio gets to be above about 0.04, photodissociation region models, so models of how the star formation photons are coming out, can no longer explain the amount of luminosity you're getting in the H2 compared to the amount of luminosity you're getting in the PAH. The PAH is just setting too low of a limit on the H2. You need something else to explain the H2 that you're getting. So what I'm plotting here is precisely that ratio versus the 24 micron luminosity. So it's got quite a range of luminosity. And all of the red points here are the radio galaxies. By comparison, normal star-forming galaxies from SINGS are these black diamonds, and you can see that they all have fairly consistent ratios that are much lower. So we need something else to explain the excess H2 emission that we're seeing, and H2 can also be excited by shocks. These are radio galaxies. We have a natural mechanism for driving shocks into the interstellar medium. This kind of emission isn't unique to radio galaxies. It's also seen, for example, in Higgs and compact groups, where there the shocks are driven by the galaxy interactions. And this is not very rare in radio galaxies. About 30% of a sample of 3 C galaxies looked at by Patrick Ogle showed this type of warm H2 emission. This kind of emission can be quite luminous, up to 10 to the 42 ergs per second, which corresponds to molecular gas masses of up to 40 billion solar masses. So it can make up a sizable fraction of the molecular reservoir in these galaxies. And when I say warm, I'm talking about temperatures between 100 and 1500 Kelvin. All right, so the specific sample that I'm looking at is 22 galaxies from a sample of Ogle and Guillard, all of which are radio galaxies, all of which have this warm H2 emission. I'm using data from the ultraviolet through to the far infrared, primarily Galax, SDSS 2MASS, Spitzer, WISE, and Herschel, supplemented where necessary with IRAS and UBV photometry from the literature in the few cases where I'm missing those data from these observations. I grab all this glorious set of images, and you can make such lovely sets of images as this set from 3C305. We start with Galax on the left, then SDSS, IRAC, PAX, and SPIRE. We determine the aperture necessary to contain all of the emission at all of the wavelengths. We apply it uniformly to all of our different data, get the photometry, and we can build up these lovely SEDs, these spectral energy distributions. We want to use these SEDs to then get things like stellar mass or star formation rates, etc. And so the program that I'm using to fit these SEDs is called Magfest. Elizabeth D'Acunha developed it. It combines stellar templates in the optical and ultraviolet with infrared templates comprised of a PAH template, a mid-IR continuum, and 2 variable dust temperature components. Fortunately, at this point, it doesn't really have an AGN component, and as you can see, 3C305 shows one of these examples where in the mid-IR you really need an additional AGN component, and so to take that part into account, I added a component by a model from Anna Sagina of an empirical AGN component. So I fit all of these galaxies. I get lovely fits, just like this one for 3C305. And out of these fittings, I get star formation rates, stellar mass, dust mass, etc. So the question that I then want to ask, well, is the star formation rate that I'm getting what I'd expect for this kind of galaxy? Is it forming stars at the same rate as normal star-forming galaxies? Now, Katie gave us a great introduction to the Kennecott Schmidt plot, where we're plotting the surface density of star formation rate versus the surface density of molecular gas. And she showed you when you have one of these galaxies that really falls off of the relation, then you can start to argue that star formation has been suppressed. We had looked at 2 galaxies of this type in detail previously, and initially it looked like, yay, both of these are suppressed by about a factor of 30. There was one tiny little niggly thing. The way that we typically get the molecular gas mass is we take a CO luminosity, we apply the glorious XCO factor that comprises all of our ignorance, and we convert from CO luminosity to molecular gas mass. When we take the molecular gas mass that we're getting in these 2 galaxies and compare it to the dust mass that we got from our SED fits, we get gas-to-dust ratios of about 1,000. A typical gas-to-dust ratio is about 100. Factors of a few, say we had gotten 300, that can be argued away. Factor of 10, that started to get a little uncomfortable. So if we instead calculate the molecular gas mass based off of the dust mass, then for these 2 galaxies, we wipe out any suppression that we see. So this was something of a concern when we started looking at our whole sample. So the first thing that we did, though, is that we take the CO luminosity, apply the typical XCO, and ask, okay, well, what is the relation what is the gas-to-dust ratio that we're getting? And we find, fortunately, that the 2 guys that we had looked at are actually really odd. They're not typical in terms of the gas-to-dust ratio that we get, and perhaps something is happening in these 2 galaxies that's further exciting the CO, which would give you the excessive CO luminosity you're getting per amount of molecular mass. But with this reassurance that for most of our galaxies, the gas mass that we're getting is fairly secure, we can put these galaxies onto the Kennecott Schmidt plot. So this is where they fall. The underlying contours are the normal galaxies that were the points on the previous plot. And then the different symbols give you an indication of how secure we are in the size of the molecular disk, which we implicitly assume is the same size as the star-forming disk. Only about 6 of the 17 that had CO observations were resolved in CO, and those are the squares. For some of the others, we can estimate the size of the star-forming disk using UV observations or the PAH, which dominates the IRAC 8 micron band. But for the others, at this point, we really don't know. And if you've got pull with ALMA, I'd be happy to get ALMA time to get good sizes. So we assume a typical size of about 1 kiloparsecs. And I'll show you in a moment the effect that it has if you increase that size. So that shows you where they fall if you use the CO luminosity. But since we don't have that for all of our galaxies, and we still want to take into account that there's uncertainty with using CO luminosity, we also place the galaxies on this plot using molecular gas mass estimated from the dust mass. And here's where they fall. So let me go back briefly to the question of scale. So this arrow shows you the effect of going from 1 kiloparsec in radius to 2 kiloparsec in radius. Because Kennecott Schmidt isn't exactly linear, you don't completely go along the Kennecott Schmidt relation, but you do go a little bit to the left for the amount that you're going down. So sure, you can, in some cases, wipe out star formation suppression by saying, okay, well, I just need to increase the radius. But often the size that you need to increase the disk starts to become a little bit ridiculous to fully explain it. So what do we see? Well, sure, some of our galaxies are falling quite a bit below the Kennecott Schmidt relation, but this isn't universally true. But for the population as a whole, we do see a shift to be below the Kennecott Schmidt, and this is particularly clear in the dust-based Kennecott Schmidt plot. To see this another way, I've plotted histograms here, where in yellow I'm showing you the normal galaxies, what were the contours in the Kennecott Schmidt. In red, I'm showing you the CO-derived positions, and in blue, I'm showing you the dust-derived positions. On the left, what I'm showing you is the offset in the horizontal. In the middle, the offset in the vertical, and on the right, I'm showing you the depletion times, which is the molecular gas reservoir divided by the star formation rate. And what we see is there is a statistical difference between the normal galaxies and our sample populations, although it's much more clear when you go with the dust-based estimates, in part because we've got greater numbers there. And what we find is that there's a suppression by about a factor of 3 in this population as a whole. So the natural follow-up question to then ask is, well, are we seeing a clear correlation between the star formation suppression and indicators of jet feedback? And so that's what I'm asking here. I'm plotting in the top row star formation rate, in the bottom row depletion time, and then on the left in blue I'm plotting the jet power. In yellow I'm plotting the diffuse X-ray luminosity, because if you recall, when the jet collides with the ISM, it creates this cocoon of hot X-ray gas around it, so perhaps by looking at the diffuse X-ray emission we might be seeing some indication of the energy being dissipated into the galaxy. In red, I'm plotting the H2 luminosity seen by Spitzer, and then in green, I'm plotting the ratio that I'm using to identify them, the H2 to the pH. These are lovely scatter plots. There are no clear correlations. The only one that might hint at it is this one between star formation rate and diffuse X-ray luminosity. But when you have star formation, you have winds from star-forming regions, you have supernovae. These contribute also to the diffuse X-ray luminosity, so that can't be attributed to the jet feedback impacting the star formation rate. So this tells us that there's no clear relationship between the amount of power that a jet might be dumping into its host galaxy and the effect that it's having on the star formation activity, and that other factors like geometry and the amount of gas that is in the system might also be playing might also be playing a role, and that it's quite a complex system. So that brings me to my conclusions. A good number of radio galaxies show this kind of emission, and these galaxies are particularly great laboratories for looking at what the impact of that feedback is having on the activity in these galaxies. The extreme gas-to-dust ratio that we saw in 2 of these galaxies are not representative of most H2 luminous galaxies, but we are seeing that star formation is suppressed by a factor of a few, and exactly how that numerically relates to the jet feedback is something that we still need to explore. Thank you.
Right, I'm going to abuse my position as chairman and ask the first question. So I completely agree with you that geometry and other confounding factors will be important here, but how are you assessing the jet power of your AGN? Because that is a difficult thing to do.
Yes. In this case, I'm using the 178 micron flux with a formula from Punsley.
Right, so it's a simple scaling from the radioluminosity. Okay.
Yes. You know, if I had cavity powers, that would be great, but...
Yeah, sure. Okay, Robert.
I was interested in the question of what fraction of these objects also have cold molecular gas, because I recognized a few old favorites. And I think that there will be a fair fraction of 20K molecular gas in there as well. Is that included in your eventual molecular gas estimate?
So the molecular gas estimate currently is based on CO luminosities or dust mass. So that's the cold. I'm actually currently working on making a version of the plot where it's total molecular gas being the cold plus the warm. So I don't have that yet.
Okay, so I got it the wrong way around. Which of those do you think is dominant? Probably cold.
It actually varies between them. In some cases, there's more warm gas than there's cold. In some cases, there's twice as much cold as there's warm. There's actually quite a wide range. In Patrick Ogle's 2010 paper, where a bunch of these galaxies come from, he has the cold gas that was known at the time, and he's got that ratio, and it varies.
Question over there? Oh, you've got the mic. Go.
Hi. So in the various scattered plots that you showed, did you try to estimate the effect of turbulence as a function of jet power, say from the dispersion in some emission lines or something like that?
That's a great question. I haven't yet. I'm sure there are optical spectra, because these are 3C galaxies by and large. I haven't looked at that because I have not worked with optical spectra. Some near IR spectra were also taken, but they haven't been looked at because they
It'll be very interesting if somebody can do this turbulence as a function of jet power and see how much of it is really coupling to the ISM and disturbing the ISM.
And it would also be interesting to see if the turbulence correlates, say, with depletion times, because you're expecting the turbulence is what's keeping the gas from collapsing.
Okay, I can see this is sparking more ideas, but we do need to move on to the next speaker. So let's thank Lauranne again.